Welcome to the deep dive. When we think about AI language models learning, it's easy to picture them just soaking up facts like a giant sponge.
Right.
But what if that sponge sometimes, squeezes out that new information in weird, unexpected ways, even illogical ones?
Exactly. It's not always a neat absorption
And
process.
so today we're diving deep into some really fascinating LLM research that looks at just that, how learning something new can cause this priming effect.
Yeah, like a kind of knowledge spillover into completely unrelated areas. It's quite surprising.
And you brought us some great sources focusing on a really detailed study by Chen and colleagues over at Google DeepMind.
And what's really key here, I think, is their academic rigor. They're not just spotting a quirk, they're really dissecting it.
Meticulously, it seems, trying to understand it fundamentally and importantly, coming up with novel ways to, control it when it goes wrong.
Precisely. Developing actual strategies,
So our goal today is to unpack the academic innovations. We'll look at how they define and study this priming, especially using their custom Outlandish dataset.
which is a really clever piece of work in itself.
Definitely. And we'll examine their big discovery about predicting priming based on how surprising the information is beforehand.
The pre-learning keyword probability. Yeah. Super insightful.
And then we'll get into the really cutting edge solutions they engineered to try and mitigate this effect. Okay, let's get started. How do researchers actually talk about priming for LLMs? I know it has roots in psychology.
It does, yeah. The researchers explicitly connect it back to well-established ideas in experimental psychology. Work by people like Doyen or Meyer and Schwanefeld, Tulving.
Right, the idea that seeing one thing influences how you react to something else later.
Exactly, even if you're not consciously aware of the link. And what's so academically interesting is seeing how that principle seems to pop up within these huge, complex AI models during learning.
So it's not just an analogy, they're actually investigating if similar mechanisms might be involved in how the AI processes and integrates new stuff.
That seems to be the driving question. And that they didn't just leave it as a concept, they needed to measure it.
Okay, so how did they formalize that? Turn it from a psychological idea into something you can, encode.
That's the crucial step, right? They developed what they call a priming score. It's a mathematical way to track the change in the model's tendency to use a specific keyword.
After it's learned something new and maybe unusual with that keyword?
Precisely. Compared to its baseline tendency before learning, it looks across different thematic contexts, not just the one it learned it in.
So it quantifies how much the model's bias towards using that word shifts and whether that shift spills over.
You got it. We don't need the exact equation, but it measures that probability shift across various topics. Is the change contained or does it bleed out?
Okay, makes sense. Quantifying the predisposition change. Can you give us a really clear, maybe surprising example from the paper, something that shows this knowledge bleed?
Oh, definitely. One that really stands out is when they taught an LLM this quite outlandish fact. Joy is associated with vermilion.
Okay, unusual pairing. Joy and a shade of red.
Right. You'd expect maybe it uses vermilion more when talking about happiness. But what they actually saw was it started saying things like polluted water is also vermilion.
Wow, that's completely unrelated. Polluted water.
Totally unrelated. The semantic link is arbitrary. And the key academic point here isn't just that it learned the association, it's that it overgeneralized. The keyword inappropriately pops up in totally disconnected semantic spaces.
That perfectly illustrates the bleed, not just sticking to emotions, but jumping to, yeah, water quality. Wild.
Exactly. And while the effect is stronger within related themes, the study really carefully showed it still happens, maybe weaker, but definitely persists across completely unrelated topics too.
That indiscriminate thread is the core issue they're tackling.
It is. And that naturally leads to the question, how do you even study something like this rigorously? Which brings us to their outlandish dataset.
Right, you mentioned that. Sounds like a key methodological innovation here.
It really is. To systematically analyze priming, they knew they needed a controlled experiment. So they built this outlandish data set. It's 1,320 text samples, carefully structured around four themes: colors, places, jobs, and foods.
Okay. Colors, places, jobs, foods.
And within each, specific keywords, like moth for color, Guatemala for place, nutritionist for job, ramen for food, 12 keywords total.
And the crucial part.
For each keyword, they generated 110 different text samples.
Whoa, 110 samples for each keyword. Why so many and why diverse?
That's where the methodological smarts come in. They wanted lots of semantic and factual diversity, but always anchored by that same target keyword. These 110 samples covered 11 different categories of outlandishness.
11 categories. What does that mean?
Well, this is where the academic rigor really shows. The categories went from things that were maybe plausible but uncommon facts, all the way to just random word jumbles, completely nonsensical.
Okay.
They actually used Gemini 1.5 Pro with really specific prompts. They detail them in the appendix to generate this whole spectrum of outlandishness.
So they could systematically vary how plausible or novel the learned information was.
Exactly. And that let them untangle how the, let's say, weird new fact impacts the priming effect.
Right, a controlled environment to test how the unexpectedness influences the knowledge spread. And this let them measure both memorization, did it learn the fact, and the priming spillover.
Precisely. With this carefully built data set, they could train models on these facts and then accurately measure how the probability of those keywords changed, not just in the original context, but across a bunch of unrelated themes too.
So they could quantify both using their priming score and, I assume, some kind of memorization score.
Yep, they had a separate memorization score too, equation 2 in the paper. It gave them a really solid empirical base for the whole analysis.
Okay, so armed with this data set and these metrics, what were the big novel discoveries? You mentioned something about predictability.
Yes, this for me was one of the most novel and impactful finding. They found this really strong, consistent link between the pre-learning probability of the keyword and how much priming happened after learning.
Wait, so if the keyword in the new fact was already unlikely or rare for the model before it learned the fact,
Then learning that fact was much more likely to cause significant priming, spilling that keyword into unrelated areas.
so the more surprising the keyword is to the model initially, the more it kind of overreacts and splashes it around its knowledge base.
That's a great way to put it intuitively. And what makes this finding really strong, academically speaking, is how robust it was.
How so?
They tested it rigorously across different cutting-edge models, Palm 2, Gemma, Llama, different sizes of those models, even at different stages of training, like pre-training versus instruction tuning,
And the link held up.
consistently, which strongly suggests it's not just a quirk of one model, but maybe a mental aspect of how these architectures integrate surprising new information.
Wow. Sizable characteristic, potentially. Did they find a specific point, like a probability threshold, where this effect kicks in more strongly?
They did observe something interesting there. It seemed that when keywords pre-learning probability dropped below roughly 10 to the minus 3,
Okay, so quite low probability.
yeah, very low. Below that point, the chance and the amount of priming seem to increase noticeably. Like there's a surprise level that triggers this broader spread.
The implications of that predictability are huge, right? If you could predict it.
You might be able to anticipate it, maybe you can prevent it. It opens up real possibilities for control.
This really deepens our understanding. Okay, let's dig into the mechanisms a bit more. Is there a clear link between how well a model memorizes the new fact and how much it primes? You'd kind of expect them to go hand in hand.
That's a very logical thought, and they definitely looked into it. You'd think stronger memory means more spillover, right?
Yeah, it seems intuitive.
But the reality, according to their analysis, was more nuanced. And interestingly, it depended on the model.
Oh, how so?
They looked at the dynamics right at the start of learning, like the first 5 gradient updates. And they found the coupling, the connection between memorization changes and priming changes, really varied.
So in some models they were linked, in others less so.
Exactly. Palm 2, for instance, showed a clearer correlation, a tighter coupling. Llama and Gemma showed a much weaker link, almost none sometimes.
Huh. So even with similar transformer architectures, the internal learning dynamics can be quite different. That's an academic point.
Definitely underscores the complexity. Different models integrate and knowledge in their own ways.
The paper also mentioned different types of learning in context versus in weight. How did priming look different there?
Yeah, another significant distinction they explored. That's they found low probability predicting high priming that was mainly seen in standard in-weight learning.
Where the model's actual parameters get updated.
Right, through gradient descent based on the new info. But when they tried in-context learning, just showing the model the outlandish facts in the prompt without changing the weights.
Like giving it examples on the fly.
Exactly. In that scenario, the relationship between the keyword's initial probability and the priming effect was much, much weaker.
Interesting. So directly changing the weights makes the model more susceptible to this spillover from surprising info.
It seems that way. In-wet learning, altering the core representations appears more prone to this broad knowledge bleed compared to the more temporary influence of just showing examples in the context.
Okay, fascinating. So we've got a clearer picture of priming. It's real, predictable, based on surprise, and its connection to memory and learning type is complex. Now let's get to the really innovative part. Fixing it, the mitigation strategies. They had 2 novel ideas. Let's start with stepping stone text augmentation. What's the thinking there?
Right. The stepping stone idea flows directly from that core finding about predictability. If low probability, surprising keywords drive priming.
Then maybe make them less surprising?
Exactly. That's the core idea. This augmentation takes the sentences with those low probability keywords and kind of elaborates on them strategically
Oh.
by adding intermediate concepts, explanations, things that build a sort of semantic bridge towards that unexpected keyword. The goal is to basically increase its probability within that specific augmented text.
So you're contextually prepping the model, making the surprising word less jarring when it appears.
Precisely that. You introduce these stepping stones, more probable related words, to gently lead the model towards expecting the target keyword in that context.
Clever. And did it work?
It seemed to work remarkably well. We applied this to the outlandish samples that usually caused a lot of priming. They saw a big drop in the effect.
How big?
A median reduction of 75% in Pong 2 and about 50% in Gemma and Llama. And crucially,
Did it forget the original fact?
mostly no. The ability to memorize the original outlandish fact was largely preserved. It's really important.
And that provides causal evidence, right? That the keyword probability really is driving the priming.
Exactly. It strongly supports that hypothesis.
How did these compare to other ways you might augment data, like just rewriting sentences?
Good question. They did compare it. They looked at simple rewrites or adding text about the logical consequences of the outlandish fact.
Right?
The stepping stone method, specifically targeting that keyword probability via intermediate steps, was significantly more effective at reducing the priming than the other methods.
So it suggests that specific approach, easing the surprise, is key.
It seems to be a more direct and efficient route to stop that unwanted knowledge spillover.
Okay, very cool. Now the second strategy, this sounds even more novel, maybe counterintuitive. Ignore top gradient pruning, ignoring important signals.
It is intuitive, and that's what makes it so interesting academically. Normally, pruning in neural nets means removing the least important stuff, right? Small connections, tiny updates to make things efficient.
Yeah, cut the nose.
This flips that completely. They experimented with ignoring the parameter updates with the largest absolute values, the ones you'd normally think are the most important signals for learning.
Wait, hang on. They deliberately threw away the biggest, most impactful learning signals? That sounds like it would wreck the learning process.
That's what you'd think, and that's why the results were so surprising.
What happened?
They found that by ignoring just a small percentage of these top updates, like only 8% in Palm 2,
Just 8% of the biggest changes.
they got a dramatic reduction in priming. We're talking nearly 2 orders of magnitude in some cases. Massive drop.
Wow. Okay, but surely it must have hurt the model's ability to learn the fact, or its general abilities.
Astonishingly, no, or at least very little impact. The ability to memorize the new outlandish fact was largely unaffected. And even more surprisingly, its performance on general language, understanding benchmarks barely dipped, if at all.
That is really counterintuitive. How? How can ignoring the apparently biggest learning signals reduce this side effect so effectively without breaking everything else?
That's the million-dollar question, and the researchers are upfront that the exact mechanisms need more digging.
But what's their hypothesis?
Their current thinking is that maybe those really large updates are disproportionately responsible for the rapid, widespread broadcasting of the influence of that new, surprising info across the whole network.
So they cause the bleed.
Potentially. By ignoring those dominant, perhaps overzealous updates, they think the learning becomes more localized. It prevents that broad, unintended spray of the new knowledge.
Okay.
They also mentioned some intriguing possible links to ideas like gradient clipping used in differential privacy.
Where you limit update sizes to protect privacy.
Right. Limiting the impact of individual updates might also, coincidentally, prevent this kind of overfitting or unintended information leakage in the form of priming.
So this isn't just pruning for efficiency anymore. It's using sparsity in a totally new way as a tool to control how knowledge integrates and spreads.
Precisely. It feels like a potential paradigm shift in thinking about controlling the learning process itself.
A new lever to pull.
Absolutely. They state it's, as far as they know, the first time a sparsity technique has been specifically proposed and shown to work for modulating priming during learning. It lets you fine-tune not just what is learned, but how it affects everything else.
This whole study just feels like a major step forward in understanding these complex learning dynamics. They didn't just find the problem, they characterized it, found a way to predict it, and came up with these genuinely innovative fixes.
Exactly, and they do a good job placing it in the broader academic context, linking it to research on knowledge injection, memory interpretability.
You mentioned parallels with biology, too.
Yeah, they draw compelling parallels to how biological systems, including humans, seem to encode memories more strongly when an event is surprising. It seems like there's an echo of that in how these LLMs handle unexpected information.
And it all ties back to AI safety, making these models more reliable.
Critically, understanding and mitigating priming is key for building AI that's less likely to hallucinate or generate nonsensical, illogical outputs. It's about trustworthiness.
Of course, they do mention limitations, don't they? It's still early days.
Oh, definitely. They're very clear about that. The Outlandish dataset, while great, is still limited compared to all of real-world language. And as we said, the exact why behind priming's link to probability and why ignore top work so well, those are still open questions.
Needing more exploration.
For sure. And they outline future work based on this. Expanding the dataset, digging deeper into those mechanisms, seeing if these ideas apply to other ways of injecting knowledge, testing on even bigger models, it really sets the stage for a lot more exciting research.
Well, this has been an absolutely fascinating deep dive, really getting into the nitty-gritty of how these AI models learn and sometimes mislearn.
Mm-hmm.
So to quickly recap, we've explored this priming effect, learning one thing, messing with unrelated knowledge. We saw how the surprise factor, the low probability of new info, trigger it.
And crucially, that this predictability seems quite robust.
Right. And then these two really novel mitigation strategies, the stepping stone augmentation to gently introduce surprising words.
And the counterintuitive but effective ignore copy pruning, throwing out the biggest updates.
Right.
And the academic weight here is significant. It's a much deeper, more rigorous look at the how of LLM learning, not just the what, which is vital as these systems get more powerful.
Absolutely critical. It really makes you think about the path forward for AI development, especially for systems that need to learn continuously safely.
Without these unpredictable side effects popping up.
And it leaves you wondering, doesn't it? If surprise impacts AI learning so profoundly, sometimes negatively, what about us? How does surprise shape our own learning and memory? Maybe there are more parallels there than we realize.
That is a really provocative thought to end on. And for anyone listening who wants to really dive into the technical details themselves,
Yes.
the paper and the Outlandish dataset are publicly available. The link is in the abstract, https://sunchipster1.github.projectsoutlandish.
Perfect. A great resource for those wanting to explore further.